So, today we will demonstrate the mutual inductance of a coil. So, how to measure mutual inductance in a laboratory. So, that we will demonstrate. So, let us discuss about the theory of this experiment. So, you know that mutual. So, this any coil has inductance. So, either the two types of inductance, self inductance L and mutual inductance M, right. So, inductance is an effect caused by the magnetic field of a current carrying conductor acting back on the conductor, So, so what does it mean? Basically, from Faraday's law of induction, it tells that any change in magnetic flux through a circuit induces an electromotive force, that is voltage, across the circuit, right. So, basically V equal to d phi by dt, change of flux with time, rate of change of flux. Okay. So, here only we have taken magnitude, there is a negative sign basically. So, just we ignore the sign. Okay. So, if you have only one coil, okay, and you are passing current through this coil, then this flux produced by this coil, okay, that is linked with this, with the same coil itself. So, in that case we will get basically self inductance, and this due to this change of flux linked with this coil itself, okay. So, it will generate voltage, electromotive force on this coil itself, right. So, basically this by definition, there is voltage induced in the same coil, that is proportional to the change of current in the same coil, okay, rate of change of the current in the same coil. So, this proportionality constant is L. So, V equal to L d I by dt. So, for single coil, okay, so that is the self inductance L. And if you have two coils, in one coil you are producing magnetic field, okay, and that magnetic field, okay, link with the nearest coil, another coil. So, if change of this magnetic field, if any change of the magnetic field in this coil, so that is that flux link with the second coil, there also it will change the flux with time, right. So, due to that, this induced EMF on this second coil, okay, that is, if that is V. So, that V is proportional to the rate of change of current in the first coil, okay. So, then this basically this induced voltage in second coil is proportional to the rate of change of current in the first coil. So, this proportionality constant is M, and it is called mutual inductance. So, basically we are going to today we are going to study this mutual inductance M, okay. So, that means it is related with the two coils. So, that is why here we have written between two plain circular coils. So, this basically, this I see, this is a coil. Yeah, you see, this coil is very important, inductor. We tell this an inductor. For producing magnetic field, we use this coil, right. So, you see here. So, this we tell this is a coil. So, there are some arrangement for connection. These two ends are connected. Here basically, here just you see wires are turned over this, wires are turned over this copper wire, okay. So, it has total turns here written, this total turns is 500, okay, and its resistance is approximately 10 ohm. Okay. So, here this connection, one connection will be here and this another connection if you take from here. So, this it is connected with 100 turns. If you, this one is a 250 and this one is 500, means this all turns are considered when you will connect between these two, half of it between these two, okay, only 100 is connected between this. So, basically here there is option, you do not need it, but it is a good option that from same coil you can vary the number of turns, okay. Number of turns whatever this you want to use, that you can select from here anyway. So, this is the coil, this simple coil, you take copper wire and just make it round, so that then it is coil, it is the inductor, okay. Now, here what that coil I was talking here, so that is basically this type of coil. So, for this experiment, now we want to find out the mutual inductance of the two coils, right. So, this so for this experiment or for the experimental geometry, we have to find out the theory working formula, right. So, yes. So, here I have written here, you see this L equal to basically mu 0 n square A by L. Mu 0 is basically the air medium, we have used no core, its a core is air. So, this is a medium, okay, air medium. So, mu 0 and n is total number of turns in this coil, okay, and A is area, cross sectional area of the coil, okay, A, and L is the length of the coil, okay, length of this coil. So, basically n by L, if you write small l, small n, so that is the number of turns per unit length. So, then small n, this is the number of turns per unit length into capital N again. So, this why this 2n is coming, so that you will that probably you will know, I will tell you. So, now for mutual inductance, so this is a mu 0 n1 n2 a2. So, number of total turns here and L1 is length of this one and this n2 is the number of turns here and a2 is area of this coil, okay. So, this is a mutual inductance, okay, expression for mutual inductance. So, if I just so working formula for our experiment, let me just first show you the setup, then it will be easy to understand the purpose of this theory, the final expression of the working formula. So, why we are taking this working formula in final form, whatever I will show you. So, that depends on basically your experimental setup. So, let me just show you the experimental setup first. So, this is the experimental setup for studying the mutual inductance, okay. So, here you see this whatever coil I show, this here two coils are kept, bigger coils, two coils are kept. This we are telling the primary coil, okay. We could do the experiment with one coil, okay, but here just two coils we kept, that to increase the magnetic field. So, it will be just double and then your signal will be higher. So, you just consider this, okay, it is just one coil, okay. Another coil just we put for for getting the uniform field, that basically we do not need, but it is better to have this type of uniform field. So, then your signal will be strong, but just consider you have one coil, either this or that one coil, and another coil in middle. Okay. So, that is so that middle one, that is the secondary coil. Okay. So, as I told, this two coil, mutual inductance between two coil. So, you can take this bigger one is primary coil and this smaller one is secondary coil. So, they are parallel, their planes are parallel. Okay. So, primary coil and that the secondary coil. Now, primary coil will, when I will pass current through the primary coil, so then it will produce magnetic field. So, I have to pass current through the primary coil. So, I need arrangement for that. So, this is the meters. Okay. This is the meter power supply, this is the function generator. So, here we will use AC current, we will use AC current because this, as we have seen, the di by dt, change of the current we require. So, that is why we will take AC current. Okay. So, this is the function, it tells function generator. You can take the either sine form of the current or some square shape of the current, square form of the current, sawtooth kind of variation of the current. Okay. So, here we will use sine wave, sine form of current. So, and here what is the, you can select the frequency of the current. Here you see already we have selected this 100 hertz. So, current, AC current of 100 hertz is coming and we have put here, here these two connections, because one is for primary coil and another is for secondary coil. So, this current, AC current, and is going to this coil, primary coil. Okay. And how much? So, it has resistance. So, how much, what is the magnitude of the current? So, that we will take reading from this ammeter. Okay. So, we have ammeter that will tell us what is the magnitude of the current. Okay. And this meter will tell us the frequency of the current, since it is AC current. Okay. Now, current is passing through this primary coil. So, when current passes through a coil, so it will generate magnetic field. So, the magnetic field will be in this the perpendicular direction to the coil. Okay. Now, that magnetic field, secondary coil is placed nearby. So, that magnetic lines of force will pass through this secondary coil. It will pass through this secondary coil. Now, that means this secondary coil is linked with flux. Now, in primary coil, this current is changing, means magnetic field is changing, means flux linked with the secondary coil, that also changing, right. So, there will be induced EMF on the secondary coil. So, that induced EMF, okay. So, so this is the these two are from this secondary coil. So, this induced EMF, okay, this voltage we have put in this oscilloscope. This is oscilloscope. So, from this oscilloscope I will know this voltage, induced voltage, whatever generated in secondary coil. So, that voltage reading I will get from this oscilloscope. Okay. So, I think its oscilloscope screen is dead. I think just let me show. Yeah, it is there. Okay. So, this is the experimental setup. Now, for this we need the working formula. For this experimental setup we need the working formula. So, that is why we have to find out. So, now theory. So, induced EMF, you know this induced EMF is basically in the secondary coil, S for secondary coil is d phi by dt. That phi is basically linked with the secondary coil. Okay. And now, so what is the flux? What is the flux? What is the magnetic field from the coil 1? So, that is Bp from primary coil, magnetic field from the primary coil. Now, this magnetic field link, this magnetic field is passing through the secondary coil. So, now flux is basically B dot A, you know, this A is the area of this coil, area of the secondary coil. So, B dot A, okay. And this is for flux is for each turn of the secondary coil. So, if number of turn is Ns, so I have to multiply with Ns. And now, this total flux link with the secondary coil, now rate of change of this flux will give you voltage. So, d by dt, right. So, by definition now Vs we have seen this equal to MSP, means secondary and primary coil, between secondary and primary coil this mutual inductance, M di by dt. So, MSP and here dIp by dt. So, Ip as if Ip takes sine form of the current, so it will be I0 sin omega t. So, then if you just differentiate it, so omega I0 cos omega t, okay. And so, Vs will be MSP and then dIp by dt will give you this, okay. And this Vs from here, so from definition I got this one, and from here Vs equal to what is this Bp? What is this Bp? What I have no. So, Vs equal to, so here you know this in Bp Ip is there, in Bp Ip is there. So, this only in this case this current is changing, right, with time, all other are constant. So, I will get dIp by dt. So, that is why that is I have written here, and rest of the part mu 0 Np, then here Ns, As divided by Lp. Okay. This is the length of the primary coil. Okay. So, then this dot product is there. So, this cos phi. What is this phi? Phi, this angle is basically between the angle, if this primary and secondary coil are parallel, this angle phi is 0. Okay. Now, this angle between this between the plane of the two coils, primary coil and secondary coil. Okay. So, if parallel then it is 0, if it is perpendicular then it is 90 degree. Okay. So, there is two coil, now when parallel this phi is 0. Now, if you change the angle, so this basically that is the phi change. Okay. Then if in perpendicular position of these two planes, that will be phi will be 90 degree. Okay. So, then basically it depends on the angle of this angle between these two coils. So, mutual inductance is a function of the phi basically. So, working formula for our experiment is basically, if you compare these two, so your Vs equal to M. So, if you compare these two, so Vs equal to MSP dIp by dt. So, which one? If Vs equal to so Vs equal to MSP, this is basically dIp by dt. So, these things I have written here. So, okay. So, this I can take as a formula for my working formula for my experiment. because this part here just I have shown there what is the MSP. MSP is basically this one. MSP. If I compare these two, then I am getting that MSP is this one. So, MSP is basically mutual inductance as a function, mutual inductance of this secondary and primary coil. It depends on the phi. Okay, it depends on the cos phi. So, MSP is basically is a function of phi. So, here if I take this on my working formula, so in CRO I can measure, in CRO I can, when I will measure this Vs, so that V maximum value, that because it is a AC signal, AC voltage. So, V max will be basically peak to peak, V peak to peak divided by 2. Okay. V peak to peak divided by 2, that will be V max, that will be V max. So, V max equal to V P by 2 equal to this part, this V, yes, I 0 omega, okay, MSP I 0 omega, and cos omega t peak to peak I have taken, right. So, peak to peak there is basically it is 1, peak to peak this value is 1 and minus 1 basically. So, difference is basically 2. So, that is why we have to divide by 2, then you can get V max. Okay. So, I 0 AC current I 0, okay, I 0 we are using this ammeter. Okay. So, there basically whatever value we will see, that is the RMS value. So, that we will see the RMS value. So, this relation between the I 0 and I RMS. So, I 0 equal to square root of 2 I RMS, right. So, this I 0 I will replace by this, okay. Then I will get MSP from here, MSP you can find out. So, this VPP divided by 2 square root of 2 I RMS omega. Now, here basically we will get reading of this frequency, this nu. So, 2 pi nu equal to omega, 2 pi nu equal to omega. So, basically here, since in our experiment instrument we will get nu, okay. So, here we will replace this omega by 2 pi nu, okay. So, now basically using this setup we are going to study, the variation of mutual inductance with angle between two plane circular coils, okay, between two plane circular coils. So, that is the experiment we are going to demonstrate now, and working formula for that is basically M as a function of phi, SP because it is just to represent primary and secondary coil. People write 1 to M, 1 to etc. So, that equal to this VPP by 4 square root of 2 pi I RMS nu. Okay. So, VPP peak to peak value we will get from CRO, I RMS that value we will get from this, ammeter, okay, and nu frequency we will get from this function generator, right. So, this is the working formula, and for the whatever the instrument you need already I have shown you. Now, let us do the experiment. So, I think so again do not confuse with these 3 coils. Effectively primary coil, one primary coil and one secondary coil is enough to study, but the signal will be this weaker because flux passing through the secondary coil it will be smaller if magnetic field is stronger. So, then obviously this flux will be higher and induced EMF will be higher. So, that is why also if you take 2 coils, so magnetic field between two coils, you will get uniform. Okay. So, this whole secondary coils will be linked with this, its whole area will be linked with the magnetic fields of equal strength. Okay. So, that is why we have taken this two bigger coil, primary coil, but that is the purpose, but one coil is enough, and whatever theory we discussing, just one coil. So, here this two coils is equivalent to one coil, only it is just giving us the two times of magnetic field. Okay. So, this coil, take primary coil 1 and secondary coil 1. Now, it is set at 0 degree, that means these two coils are parallel. Okay. These two coils are parallel, primary and secondary coils are parallel. Okay. For this, so what we will do, we will vary the phi angle between these two coils, and for each angle we will take the reading. We have to find out the mutual inductance for each angle. So, then we will plot the mutual inductance. Basically, our aim is to plot mutual inductance versus phi. Okay. Mutual inductance versus phi. So, that is what we are interested to study, to demonstrate here. So, to calculate this one, so so this current is, will fixed current, will fix this frequency. Now, only we will vary this angle phi, then this VPP will vary. So, now that VPP reading we will get from their oscilloscope, and then we will put here, then for each angle VPP will be different. So, I have to note down basically angle versus VPP or VPP versus angle, that is what I have to note down for a particular value of nu and current I RMS. Okay. So, here you can see we have put this RMS, this the I think scale we have taken 100. So, that means top scale. So, current is around 65, around 60, yeah, I have to take this 66 milliampere. This current is milliampere. The scale we have taken is a milliampere. Okay. So, this current we have fixed. Now, here we have taken this AC current, its frequency also we have fixed here, that is 100 hertz. So, that you have to note down first. For this nu and IRMS, now we are going to study, we are going to find out the mutual inductance, or we are going to find out the voltage VPP for different angle of phi. Okay. And here we have column serial number. So, phi will vary 0 to 180 with the 10 degree change step or 5 degree step, whatever you prefer. VPP. So, basically here I forgot to, so later on just I put this column. So, twice we will take reading. So, when we are increasing the angle 0, 10, 20, 30, 40 up to 180. Okay. So, we will take reading VPP. Then again, so that is phi increasing. So, during increasing of phi, I will take VPP reading, and then again during the decreasing of phi from 182, again I will come back to 0 in with same step. Okay. So, during that again I will take reading. Okay. Now, we can take average of these two reading, and then we will get mean reading. So, that will be the VPP for each angle, and IRMS, I should note down, this is IRMS, it is the 66 milliampere, 66 milliampere as my reading is here, and that frequency is the 100, I have to write this 100. Okay. So, now here it's the take reading for 0 position, take reading this for 0 position, this the here you see it is giving reading, okay. It's the VPP 6.15 volt. It is giving 6. I have to see properly. Yes, I think 6.20. It's changing. So let me write 6.20. So for 0 angle, now this for this 6.20. Okay. And also you have to note down the least count of this instrument. Least count of this one, what is the that you have to note down is the I think 0.01 volt, 0.01 volt. That is the least count of that one. Okay, that means 10 millivolt. Least count of that one, and least count of this one is 2 milliampere. Least because each division is 2 milliampere. So least count of phi, it is I think here it is in 1 degree. Yes, you cannot see probably, but I can see this 1 degree. So here I will write least count. So not centigrade, it's the 1 degree. Least count of phi 1 degree. Least count of IRMS, this is as I told, this is the 2 milliampere. 2 milliampere, that I have to write 2 milliampere. Least count of VPP is the 0.01 1 volt, means 10 millivolt, and least count of nu. So it's a by 0.1 hertz, it's a 100.1. So it's a 0.1 hertz, 0.1 hertz. Okay. So least count of your instrument, that you have to note down. Okay. So now everything you have noted down. Now just vary and take the reading of this one. So I will go in 10 degree step. So I will go to the next step. So it's So I change it with 10 degree. You see what is the value? Just I have to select auto, then automatically it will give value. I think it's it is giving 6.08. So for 10 degree you write for 10 degree 6.08. Okay. So similarly I will change to 30 degree, then 40, 50, 60. Let me go to the 90 degree. So for each 10 degree I will take point, but I will not take reading for all. I think I have to go, you see, it's a 90 degree. With this primary coil, this secondary coil, primary coil is this, now secondary coil is this. Secondary coil is this, so it should be 0. So it's more or less 0, it's more or less 0, I think perfectly you have to make it. Yes. Or I have to take it auto, then to perfectly, no. Oh, it just changed the scale. Okay, it has come to the millivolt, so that's why. Anyway, okay. So it's you see here reading it is showing 1.9, it means 2 millivolt. It's showing 2 millivolt. So error bar is 10 millivolt. Okay. So this 2 millivolt is a error noise. Okay. So this we can take reading 0. Okay. So this up to 90 degree. Then again you just change 100, 110 up to 180. Take the reading, write the reading during increasing of phi. Now again you come back to from 180 to 170, 160, then again 90, and then up to 0. Okay. So you are changing the angle, your angle is decreasing. So during that time you take reading and then find out the mean. And this VPP you know now. So working formula, just for each value of work, this VPP, you calculate this. mutual inductance. It is in Henry or millihenry. It should be in millihenry, I guess. It should be in millihenry. Okay, better to write in millihenry or Henry, but into 10 to the power minus 3 kind of things you have to write. Okay, so this way now this phi versus this mutual inductance, this data is available, just plot it. And this is a very familiar curve for this mutual inductance. So, whether you see this, whether you are getting this type of curve or not. So, that is the experiment that you are studying the variation of mutual inductance with angle between two plane circle coils. So, this is the experiment I demonstrated, right. So, I think yes, and if you want to calculate the error, so this is the error working formula, and error there del VPP by VPP plus in error in I and then error in nu. Okay. So, all delta nu, delta I, delta V, you know, we have noted down, just put it and just choose a particular angle. For that angle, you have mutual inductance, and what is the error on this mutual error, you can just tell. Okay. So, I think I described this experiment. This is very easy and small experiment, very good experiment. Okay. So, I think I will stop here. Thank you for your attention.